There is a cliff on a moon of Uranus so high that if you jumped, it would take you a full 12 minutes to hit the ground. There is a planet where it rains diamonds, and another that is so dark it would swallow the light from your flashlight without reflecting anything. In the next 2 hours, we won't assume anything. We will visit the largest water reservoir in the universe floating in the void. We will see stars that visually trick you by multiplying fourfold. And we will understand why there is an invisible force, the Great Attractor, pulling us all right now at impossible speeds. If you think the universe is a quiet place, wait until you hear what it has to say. What does the universe smell like? Although it may seem like an impossible question, science has given us surprising clues. At the center of our galaxy, the Milky Way, there is a cloud of gas and dust called Sagittarius B2. Astronomers have discovered that this cloud is filled with complex chemical compounds, and among them, ethyl formate stands out. This compound is responsible for the raspberry aroma and the flavor of rum on Earth. So, if we could smell the heart of the galaxy, we would be greeted by a familiar scent, a mix of sweet fruits and a hint of alcohol. But how is it possible to know what a cloud smells like over 25,000 light-years away? The answer lies in spectroscopy, a technique that allows us to identify the elements and molecules present in space by the way they absorb and emit light. Scientists compare the chemical fingerprints of these molecules with those of known substances on Earth. That's how they discovered ethyl formate and other compounds like acetic acid, which we can also find in vinegar. Interstellar chemistry is much more varied and rich than we could imagine. However, not everything in the universe smells like dessert. Space also contains molecules like hydrogen sulfide, which on our planet is associated with the unpleasant smell of rotten eggs. On giant planets and moons in our solar system, extreme conditions allow for the formation of even more exotic compounds, some of which would be toxic or unbearable for our sense of smell. If you could ever smell the atmosphere of Titan, Saturn's largest moon, you would perceive a mix of hydrocarbons, something like gasoline and burnt plastic. Does this mean that if we floated in space, we could perceive these aromas? Not exactly. The vacuum of space prevents molecules from traveling to our sense of smell. However, astronauts who have conducted spacewalks have reported another curious phenomenon. Upon returning to the spacecraft, their suits emit a metallic odor, similar to electric welding or ozone after a storm. This peculiar scent comes from molecules excited by radiation and extreme vacuum, which react upon coming into contact with oxygen inside the space station. Thus, although we may never be able to smell space directly, cosmic chemistry continues to surprise us and challenge our imagination about the senses in the universe.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey.
Can it rain diamonds? Although it sounds like fantasy, in the universe, reality often surpasses fiction. On Neptune, the blue giant of our solar system, the conditions are so extreme that scientists believe diamonds rain down from the upper layers of its atmosphere to the core. How is this possible? The pressure and temperature deep within Neptune are so high that carbon atoms are compressed and crystallized, forming solid diamonds that slowly fall toward the planet's interior like precious stones in an endless storm. It's a process we could never witness on Earth, where the pressure needed to produce this phenomenon only exists in the depths of our planet and never in the atmosphere. But the extraordinary doesn't end there. More than 60 light-years away on the exoplanet HD 189733b, one of the deadliest and strangest rains in the cosmos occurs. This planet, the size of Jupiter, orbits so close to its star that its atmosphere reaches temperatures of up to 1,700 degrees Celsius. The result? It doesn't rain water, not even acid, but molten glass. The wind, blowing at over 7,000 kilometers per hour, carries tiny droplets of molten silicate, scattering them from side to side of the planet in a sideways storm of burning glass. Imagining a world where the sky could literally cut you to pieces reminds us of how inhospitable and diverse the landscapes beyond our Earth can be. What do these extreme phenomena imply? In reality, they reveal how chemistry and physics can create scenarios completely alien to human experience. On Neptune, the available carbon and the right pressure are the recipe for diamond rains, while on HD 189733b, the combination of searing heat and silicon-rich materials leads to glass rains. It's as if each planet has its own recipe for disaster, dictated by its position, composition, and proximity to its star. These impossible rains invite us to rethink what we understand by weather. While we complain about the rain here, in other parts of the universe, water would be the least of our problems. Can you imagine an umbrella capable of protecting you from a storm of diamonds or molten glass? The vastness and creativity of cosmic nature show us that, in the universe, the impossible is just a matter of perspective. Can a storm take the shape of a perfect geometric figure? On Saturn, the answer is yes. At the north pole of this gas giant lies one of the most enigmatic phenomena in the solar system, Saturn's hexagon. It is neither an illusion nor a mere whim of the clouds. It is a cloud structure over 20,000 kilometers wide, with 6 almost identical sides, rotating unperturbed for decades or even centuries. How is it possible that nature, so chaotic and disorderly at times, produces a shape as precise as that of an almost perfect hexagon? The secret of the hexagon lies in Saturn's turbulent atmosphere. There, winds blow at speeds that can exceed 300 kilometers per hour in circular patterns around the pole. But instead of forming a simple whirlpool, as a hurricane would on Earth, the conditions on Saturn transform that current into a standing wave, creating the 6 defined sides of the figure. It's as if a river of air spinning at high speed began to undulate, and for reasons still being studied by science, those waves froze into a hexagonal structure. A laboratory experiment can recreate this effect. When a fluid spins in a container and conditions are adjusted, polygonal shapes can form, such as triangles, squares, or hexagons. Saturn, on its colossal scale, is a natural laboratory that surpasses any earthly experiment. And what lies at the center of the hexagon? A gigantic storm, almost as large as Earth, marking the planet's axis of rotation. The hexagon rotates along with Saturn, completing a turn in approximately 10.5 hours, but it never loses its shape or position. The most surprising thing is that, while clouds and storms on other planets change and dissipate, the hexagon remains stable and firm, as if defying the laws of atmospheric chaos. Even its color can vary with the seasons. At times, the hexagon appears blue, and at others, golden or brown, due to changes in sunlight and particles in the atmosphere. Saturn's hexagon remains an enigma for astronomers. Why does only Saturn display such a marked phenomenon? Could similar figures exist on other giant planets? Its existence reminds us that, even amidst the apparent disorder of the universe, nature is capable of creating patterns of astonishing beauty and precision, as if the cosmos were playing the role of both artist and mathematician at the same time. Miranda, one of Uranus's most enigmatic moons, is a true natural laboratory of cosmic oddities. What makes Miranda so special among the more than 170 known satellites of the solar system? Its surface looks like the result of a gigantic puzzle, with cliffs and canyons that defy imagination. But there is one place that stands out above all: the Verona Cliffs, the tallest ever observed in the solar system, with an estimated height of up to 20 kilometers. That is, more than double the depth of the Mariana Trench on Earth, or about 10 times the size of the Grand Canyon in Colorado. Now think about this. What would happen if someone dared to jump from the top of the Verona Cliffs? On Earth, a fall like that would be lethal in a matter of seconds. But on Miranda, everything is different. The gravity is so low, barely 1% of Earth's, that a jump from that height becomes an almost surreal experience. The descent would take approximately 12 minutes, enough time for you to reconsider all your life decisions before reaching the bottom. During the fall, the acceleration would be so gentle that the journey would feel like a slow dance toward the abyss, more like floating than falling. And what happens upon reaching the end of the journey? Surprisingly, the impact speed would be similar to that of a person jumping from a diving board at an Olympic pool on Earth. In other words, although the height is staggering, gravity softens the landing, and the impact would, in theory, be survivable. This phenomenon is due to the fact that, on small celestial bodies like Miranda, the force of gravity is so reduced that falls transform into leisurely journeys, almost as if time stretches. Miranda not only challenges our perception of the extreme, but also illustrates how the laws of physics can shape scenarios that seem straight out of science fiction. The Verona cliffs are a reminder that the universe is full of places where the impossible becomes commonplace and where a leap of faith can last an eternity. Who would imagine that, far from Earth, an endless fall could actually be one of the softest experiences in the solar system? Is it possible for a planet to exist that reflects less light than coal? The answer is yes, and its name is Tres 2b. This exoplanet, located about 750 light-years from Earth, is one of the most mysterious and extreme worlds discovered outside our solar system. But what makes Tres 2b so special? The key lies in its incredible ability to absorb light. While most planets reflect some of the light from their star, Tres 2b barely returns a tiny fraction to space. It only reflects about 1% of the light it receives. It is so dark that if you could get close to it, it would be like looking at a floating ball of ink in space. But how can a planet be so black? The explanation defies our intuition. Tres 2b is a gas giant similar in size to Jupiter, but it orbits so close to its star that its atmosphere reaches temperatures exceeding 1000 degrees Celsius. Despite this extreme heat, its surface does not shine as one might expect. This is because its atmosphere likely contains chemical compounds like vaporized sodium and titanium oxides, which absorb visible light extraordinarily efficiently. It's as if it were covered by a layer of ultra-durable black paint, capable of devouring almost all the light that hits it. However, this dark planet is not completely invisible. Although it absorbs visible light, it emits a faint reddish glow due to its scorching temperature. Imagine a piece of glowing coal in a forge. It does not reflect light, but it glows faintly from its own heat. Thus, astronomers can detect it by following that faint infrared flicker using telescopes capable of capturing the subtlest signals from the universe. Tres 2b shows us that in the cosmos, the rules are not always what we imagine. Why would nature create such a dark planet in such an extreme environment? The answer is still not definitive, and each finding about this world challenges the limits of our understanding of planet formation and diversity. This exoplanet is a reminder that even amid the brightness of stars, there are places in the universe where absolute darkness reigns. Can a star be older than the universe itself? This question seems like an impossible riddle, but science has encountered a mystery like this: the star Methuselah. Officially known as HD 110283, this star is located in the constellation Libra and has puzzled astronomers for decades. Why? Early calculations of its age suggested it was about 14,600,000,000 years old, while the estimated age of the universe is 13,800,000,000 years. How is it possible for a star to be older than everything that exists? The enigma of the Methuselah star arises from the precision with which scientists can measure stellar ages. To calculate its age, astronomers analyze the light it emits and its chemical composition. Methuselah is a metal-poor star, meaning it formed when the universe was young and there weren't many heavy elements yet. This fact suggests that it is one of the first generations of stars, almost a living relic of cosmic origins. But how reliable are these dating methods? The measurements are based on models and assumptions, and a small error in distance or composition can alter the calculated age by hundreds of millions of years. The Methuselah paradox has led scientists to refine both their stellar evolution models and the ways to measure the expansion of the universe. In fact, By improving the precision of observations and correcting some factors, the estimated age of the star was slightly reduced, coming very close to the calculated age of the universe, but still brushing against the limit. Does this mean there is something wrong with cosmological theories, or simply that our tools are not perfect? The answer remains debated, but what is certain is that these apparent contradictions drive science to improve and to question what we take for granted. Ultimately, Methuselah is more than just an astronomical curiosity. It is a reminder that, even with all our current technology and knowledge, the universe still holds secrets that challenge our understanding. Are there other stars as old, scattered like silent witnesses to the birth of everything? The search continues, and each discovery like this brings us a little closer to understanding the true origin and destiny of the cosmos. Did you know that there is a substance so strange and powerful in the universe that if you tried to break a piece the size of a sugar cube, you would need a force greater than what all of humanity could generate? This substance is called nuclear pasta, and it forms in one of the most extreme environments known, the interior of neutron stars. But what exactly is nuclear pasta, and why does it fascinate astrophysicists so much? When a massive star explodes as a supernova, its core collapses and gives rise to a neutron star, an object so dense that its mass, comparable to that of the Sun, fits into a sphere just about 20 kilometers in diameter. Under these conditions, atoms are crushed and electrons merge with protons, resulting in an ocean of neutrons. However, in the intermediate layers of these stars, matter is neither completely liquid nor completely solid. It is here that nuclear pasta emerges, a series of exotic structures formed by protons and neutrons that take shapes reminiscent of Italian pasta, such as spaghetti, lasagna, and gnocchi. Why does matter organize itself in such a peculiar way? The answer lies in the intense competition between two fundamental forces: the nuclear force, which holds nucleons together, and the electric repulsion between protons. Under the extraordinary pressures of neutron stars, these forces cause nucleons to cluster into geometric patterns, optimizing space in a way as efficient as a beehive, but at a subatomic level. Thus, lasagna layers, spaghetti tubes, and gnocchi spheres are born, structures with cute names, but with a strength and density beyond any earthly scale. The most surprising thing is that nuclear pasta could be the strongest matter in the universe, up to 100 billion times stronger than steel. Scientists believe that these structures may influence how neutron stars emit gravitational waves and light, and could be responsible for strange phenomena such as X-ray bursts or the mysterious periodic signals we detect from Earth. Although we will never be able to manufacture or touch nuclear pasta on our planet, its study opens a window to the most extreme properties of matter and reminds us that even in the most inhospitable corners of the cosmos, nature finds astonishing ways to organize itself. How far can our understanding of nuclear pasta go? Each advance in this field not only challenges our imagination, but also brings us a little closer to deciphering the secrets of the densest and most mysterious objects in the universe. In that natural laboratory that are neutron stars, matter becomes a puzzle of shapes and forces that redefine the limits of the possible. What if I told you that there are planets wandering alone through the galaxy without a star to illuminate them or a solar system to belong to? These mysterious bodies are known as rogue planets or orphan worlds. Unlike planets that orbit a star, these cosmic vagabonds float freely in the darkness, like ships adrift in an infinite and silent ocean. Their existence raises a fascinating question. How did they become so isolated in the vast universe? The most accepted explanation is that many of these planets were born in solar systems, just like Earth, but were ejected due to violent gravitational interactions. Imagine a cosmic billiards game, where planets compete for space, and sometimes one gets shot out into the interstellar void. Another possibility is that some worlds formed independently from clouds of gas and dust, never igniting like stars. Whatever their origin, these rogue planets are more common than we think. Some studies suggest they could be as numerous as the stars in the galaxy, or even outnumber them. These planets are incredibly difficult to detect. Not emitting their own light or reflecting that of a nearby star, they remain hidden in the darkness, invisible to most traditional telescopes. However, the gravitational microlensing technique, which leverages the effects of gravity to amplify the light from distant objects, has allowed astronomers to discover several of these solitary worlds. Each finding is a reminder of how little we know about the variety of planetary scenarios that exist beyond our solar system. Could these orphan worlds harbor life? Although the idea seems unlikely, some scientists do not completely rule it out. If a rogue planet retains enough internal heat, generated by geological processes, or a dense atmosphere, it might be able to maintain underground oceans protected from absolute freezing. Thus, life, in its most resilient form, could find refuge even in the most inhospitable and lonely places of the cosmos. Orphan worlds remind us that the universe is full of surprises and stories yet to be discovered, waiting in the darkness between the stars. What if I told you that, somewhere in the universe, there exists a diamond so large that it would make any jewel on Earth seem insignificant? This colossus is not found in a safe, but in the heart of a dead star called BPM 37093, nicknamed by astronomers as Lucy. But how is it possible for a star to become a giant diamond? To understand this, we must first explore the fate of stars like our Sun. When a star similar to the Sun exhausts its fuel, it expels its outer layers and leaves behind its core, a white dwarf. Inside these white dwarfs, temperatures and pressures are so extreme that the carbon within begins to crystallize, literally forming a diamond structure. In the case of Lucy, this process has resulted in a core of crystallized carbon and oxygen weighing around 10,000 trillion carats, far surpassing any diamond one could imagine. Now, what does this mean for us? Besides being a fascinating curiosity, Lucy is a cosmic time capsule. White dwarfs like her allow us to study the life and death of stars, and thanks to their composition and cooling, we can calculate the age of stellar systems. It's as if the universe has left us diamond-made clocks, marking the passage of eons with astonishing precision. But there's more. The existence of Lucy reminds us that the most precious and beautiful elements of the cosmos, like diamonds, are forged in the most extreme scenarios. In fact, the carbon that is part of our own bodies was created in the hearts of stars that have long since died. That's why, every time we admire the sparkle of a diamond, we are contemplating a small reflection of the process that occurs on an astronomical scale, where time, gravity, and physics transform stardust into true wonders of the universe. Did you know there is a place in the universe where there is enough water to fill all the oceans of Earth, more than 100 trillion times? In the depths of the cosmos, astronomers discovered a gigantic reservoir of water vapor around a quasar, an object so extreme it seems straight out of science fiction. More than 12 billion light-years away, this quasar, named APM 08279 Pli 5255, holds the largest amount of water ever detected outside our galaxy. But how is it possible to find an ocean around a supermassive black hole? To understand this, we first need to know what a quasar is. Imagine the core of a galaxy, where a supermassive black hole devours matter at a furious pace. This matter, as it falls, heats up and releases energy so intense that it eclipses the entire galaxy surrounding it. Quasars are, in essence, the brightest beacons in the universe. But what's astonishing is that in the environment of one of these cosmic monsters, a cloud of water vapor has been detected with a mass equivalent to about 140 trillion times that of all Earth's oceans combined. The presence of water in such quantities raises fascinating questions. How can water survive in such an extreme environment, where radiation is colossal and temperatures reach hundreds of degrees below zero? The answer lies in the physics of the quasar itself. The intense radiation and heat generated by the black hole keep the water vapor in a gaseous state, allowing it to extend across hundreds of light years. Thus, the water does not form a liquid ocean like those we know on Earth, but rather an immense nebula of vapor invisible to the naked eye, yet detectable with radio telescopes. This finding not only challenges our imagination, but also provides crucial clues about the evolution of the early universe. The fact that so much water existed when the cosmos was still young indicates that the essential ingredients for life, such as hydrogen and oxygen, were already present and combining under the most unusual conditions. Could water be as common in the universe as it is on our planet? The existence of this galactic ocean suggests that water, far from being a rarity, might be much more widespread than we think, even in the most unexpected and violent corners of the cosmos. Thus, the ocean of the quasar reminds us that the universe is full of surprises. Where we thought there could only be emptiness and destruction, we find the key to one of the most valuable elements for life. And as scientists continue to trace signals of water throughout the vastness of space, it becomes clear that the secrets held by the cosmos are as deep and vast as the ocean surrounding that distant quasar. What mysterious force could be pulling our galaxy, along with thousands of others, toward an invisible point in the universe? This is the unsettling question that has puzzled astronomers for decades. We call this enigma the Great Attractor. It is not an object with a defined shape or a bright celestial body, but rather a region of space that, for reasons still not entirely clear, exerts a powerful gravitational influence over a vast area of the local universe. It's as if a hidden current, imperceptible yet irresistible, guides the movement of everything around it toward an unknown destination. How was this invisible force discovered? At the end of the last century, scientists began to notice that galaxies, including the Milky Way, were not only moving away from each other due to the expansion of the universe, but they also seemed to be deviating from that path, as if something were pushing or pulling them in a specific direction. By analyzing the speed and trajectory of thousands of galaxies, they realized that all shared a common motion, pointing toward a region of space located about 250 million light-years away in the constellation Centaurus. But what is really in that place? Surprisingly, the answer remains a mystery. The region of the Great Attractor is hidden behind the so-called galactic plane, a densely populated area of stars, gas, and dust from our own galaxy that blocks direct vision. However, with observations at wavelengths that penetrate the dust, such as X-rays and radio waves, astronomers have detected clusters of galaxies and enormous concentrations of dark matter in that direction. It is estimated that the total mass in the Great Attractor region exceeds that of hundreds of thousands of galaxies combined, enough to alter the movement of gigantic cosmic structures over millions of years. Does this mean that the Milky Way and its neighbors are destined to be consumed by this force? In reality, the Great Attractor is not a black hole or a deadly trap, but a consequence of the uneven distribution of mass in the universe. As we advance in our understanding, we discover that the universe is not homogeneous. There are superclusters, voids, and filaments, and the Great Attractor is just one piece of an even larger puzzle. In fact, recent research suggests that the Great Attractor itself is being pulled toward an even more colossal structure called the Shapley supercluster. Thus, our cosmic journey is part of a much larger dance, guided by invisible forces that remind us of how little we know about the deep architecture of the cosmos. What if there were a place in the universe where, when you looked around, you saw absolutely nothing? No stars, no galaxies, not even a faint cloud of gas. Such is the extreme nature of the Boötes Void, one of the most mysterious and desolate regions of the cosmos. It is a gigantic cosmic void, a kind of bubble in space, so large that it could hold several Milky Ways side by side and still have room to spare. Astronomers discovered it in the 1980s, and since then, the Boötes Void has left scientists around the world puzzled. The question is inevitable. How can such an empty region of the universe exist? The Boötes Void measures approximately 330 million light-years in diameter To put it into perspective, if our galaxy were the size of an orange, this void would be like a completely empty football stadium, with only a few marbles scattered here and there. While in other parts of the universe, galaxies cluster into groups and filaments. Here, solitude is the norm. Astronomers estimate that it contains about 60% fewer galaxies than would be expected in a region of that size. What accounts for such an absence? The most accepted theories suggest that during the early formation of the universe, fluctuations in matter density caused some regions to remain almost empty, while others became enriched with matter and gave rise to clusters of galaxies. However, the Botas void is so vast and uniform that it challenges conventional explanations. Some scientists have even joked that if our civilization were located at the center of that void, we probably wouldn't even know that other galaxies exist. The night sky would be so dark and empty that the idea of a universe filled with stars would be nothing more than a fantasy. But even in this apparent cosmic desert, science finds reasons to marvel. The study of voids like Botas allows astronomers to test their theories about the large-scale structure of the universe. Additionally, these voids act as natural laboratories to investigate the influence of dark matter and dark energy, the most enigmatic components of the cosmos. Thus, the Botas void is not only a symbol of solitude, but also a gateway to the deeper mysteries of the universe. What if I told you that in the universe, gravity can do something as amazing as bending light? This is not a magic trick, but a real and proven phenomenon: gravitational lensing. However, there is a case so peculiar and visually striking that science has given it a name almost poetic: the Einstein cross. Why can the light from a single galaxy be split into 4 identical images, forming a perfect cross in the sky? It all begins with Albert Einstein's theory of general relativity, which taught us that gravity is not simply a force that attracts objects, but a curvature of space-time itself. When a distant galaxy emits light and, on its way to us, another massive galaxy intervenes, the gravity of the latter acts like a gigantic cosmic magnifying glass. But, unlike a normal magnifying glass, gravity can bend light in several directions at once. Thus, depending on the exact alignment between the distant galaxy, the intervening galaxy, and Earth, we can see the light from the same source multiplied in several positions. The Einstein cross is one of the most spectacular examples of this effect. It involves a galaxy located about 8 billion light-years away, whose light is bent by a closer galaxy about 400 million light-years from us. The result is that, from our perspective, we see not 1, nor 2, but 4 images of the same galaxy, arranged in the shape of a cross around the core of the galaxy, acting as a lens. Can you imagine looking up at the sky and seeing the same source of light repeated 4 times? It's like seeing a multiple reflection in the mirrors of a dressing room, but on an unimaginable cosmic scale. This phenomenon is not only visually impressive, but it is also a fundamental tool for modern astronomy. Thanks to the Einstein cross and other gravitational lenses, scientists can measure the mass of galaxies that would otherwise be impossible to weigh. Moreover, they allow us to study dark matter, that mysterious, invisible component that makes up most of the universe. How is it possible for light to travel along such different paths, yet arrive at us almost at the same time? The answer lies in the curvature of space-time, which can twist and multiply light rays in a precise and astonishing choreography. The Einstein cross is a tangible proof that the universe is much stranger and more fascinating than our intuition might suggest. It reminds us that gravity not only governs the movements of planets and stars, but can also transform the way we see the cosmos. Observing a cross of light formed by gravity is, in a way, peering into the most sophisticated tricks that nature has in store for those who look closely. Did you know that the center of our galaxy, the Milky Way, hides a pair of invisible giants that defy all logic? These are the Fermi bubbles, 2 enormous lobe-shaped structures that emerge above and below the galactic core, stretching over 25,000 light-years. To put it into perspective, if our galaxy were a city, These bubbles would be like two colossal balloons floating above and below its center, covering a distance that defies any attempt at human scale. But what are they really, and how did they form? The Fermi bubbles were discovered in 2010 thanks to the Fermi Gamma Ray Space Telescope. Interestingly, even though we can't see them with our eyes, they emit such intense energetic radiation that it stands out in high-energy sky maps. Where does that energy come from? Scientists believe it could be the result of colossal explosions that occurred in the past, perhaps fueled by the supermassive black hole residing at the center of the Milky Way. Imagine a source so powerful that in just a few million years, it expelled jets of particles and radiation at speeds close to the speed of light, inflating these bubbles like cosmic balloons. Could these bubbles be formed from the remnants of millions of stars devoured by the central black hole? A fascinating hypothesis suggests that every time the black hole feeds, it releases energy in the form of jets and galactic winds, pushing gas and plasma to enormous distances. Another theory posits that a series of supernova explosions near the galactic core could have contributed to the formation of these structures. Whatever the exact origin, the fact is that the bubbles continue to emit gamma rays, the most energetic form of light in the universe, as if they were invisible beacons marking the past and present activity of the galactic heart. The most surprising thing about the Fermi bubbles is their symmetry and size. If we could travel in a ship at the speed of light, it would take us about 25,000 years to cross from one end to the other of just one of these bubbles. And yet, until recently, we didn't even know they existed. What other secrets does the core of our galaxy hide, waiting to be discovered by future generations of astronomers? The Fermi bubbles remind us that, although the universe may seem silent at first glance, it is actually full of energetic scars, witnesses to violent events that shape the history of galaxies. Did you know that every time you look up at the sky, you are actually looking into the past? It may sound incredible, but light does not travel instantaneously. Everything we see in the universe is an old photograph, a postcard sent from such vast distances that light takes years, centuries, or even billions of years to reach us. For example, when we observe the moon, we see it as it was just a little over a second ago, because that is how long it takes for light to travel the distance between it and Earth. Now think about the sun. Even though it is so present in our lives, what we see is its version from 8 minutes ago. If for some reason the sun were to suddenly disappear, we would still see it shining and feel its warmth for those 8 more minutes before reality caught up with us. And if we look at the closest star, Alpha Centauri, the light we perceive today left it over 4 years ago. It's almost like receiving a letter sent from another city, except instead of paper, the information travels in the form of light. But the real magic happens when we point our telescopes into the depths of space. There are galaxies so far away that their light has taken billions of years to reach us. This means we see them as they were when Earth didn't even exist, when the universe was young and the first stars were just beginning to shine. Observing those distant points is like opening a window to the childhood of the cosmos, allowing us to study its evolution and oldest secrets. Thus, every night we look at the stars, we actually become time travelers, explorers of stories written in light. Everything we see in the universe is the past, and the farther we look, the further back in time we find ourselves. The night sky is, in essence, the oldest visual archive we can consult, and each star, each galaxy, tells us a different chapter of the universe's history. Why, if the universe is filled with stars, does the night sky not shine like the sun in every direction we look? This is the intriguing question at the heart of Olbers' paradox, a puzzle that has baffled astronomers and thinkers for centuries. If the cosmos were infinite and eternal, with stars evenly distributed throughout space, it would seem logical to think that, no matter where we looked, our line of sight would eventually, sooner or later, encounter the surface of some star. The result would be a sky so bright that night would be impossible. However, every night, when we look up, we find ourselves surrounded by overwhelming darkness, barely sprinkled with tiny points of light. What is it that fails in the logic of an eternally illuminated universe? To understand this, we must first consider the speed of light and the age of the universe. Light, though fast, has a limit. It travels at about 300,000 kilometers per second, but the universe, according to modern cosmology, has a finite age of about 14 billion years. That means we can only see the light from stars whose radiation has had enough time to reach us since the Big Bang. But there's more. The universe is not only young in cosmic terms, but it is also expanding. As space stretches, the light from distant galaxies shifts to longer wavelengths, moving away from the visible spectrum and becoming infrared or even radio. Thus, although there are countless stars beyond our observable horizon, their light has either weakened or shifted to become invisible to our eyes and optical telescopes. Olber's paradox is not just an astronomical riddle, it is a window into the true dynamic nature of the cosmos. It tells us that the night sky is dark because we live in a universe finite in age, constantly expanding, with regions so far away that their light has not yet reached us, or perhaps never will. In other words, the darkness of the night is a direct consequence of the history and evolution of the universe itself, and each star we see is just a small sample of all the light that ever existed, much of which is still on its way to us. So the next time you contemplate the vastness of the night sky, remember that this darkness is not absence, but evidence. The proof that the universe had a beginning is in motion, and, paradoxically, its light tells us a story of times and distances that challenge the imagination. Olber's paradox is, in essence, an invitation to look beyond the obvious and question the depth of the mysteries that still surround us. Have you ever wondered how everything will end? Not just the Earth or the Sun, but the entire universe. Scientists have proposed that in billions of years, when all the stars have exhausted their fuel and the galaxies are merely scattered memories, the cosmos will enter a stage known as the era of black holes. But what does this really mean? Imagine a dark, cold, and almost empty universe where the protagonists are no longer shining stars, but invisible and hungry colossi, black holes. During this era, black holes will be the last cosmic titans. There will be no light from stars or warmth, only the relentless gravity of these objects that devour everything in their path. But how long can black holes survive in such a desolate universe? Here comes a phenomenon as strange as it is fascinating: Hawking radiation. Proposed by Stephen Hawking, this theory suggests that black holes, far from being eternal, emit a faint radiation and gradually lose mass. Over an almost inconceivable amount of time, even the most massive black holes will eventually evaporate, disappearing in a final explosion of energy. Can you imagine what it means to wait so long? A supermassive black hole could take up to 100,000 trillion years to evaporate. If the history of the universe were a single day, the era of black holes would literally occupy the entire night and beyond. However, in this seemingly static period, unusual events occur. From time to time, two black holes may encounter each other and merge into one, releasing gravitational waves that travel through the void, vibrations in the very fabric of space-time, as if the universe still remembers its youth. At the end of the era of black holes, only subatomic particles will remain, floating in the darkness. This is the so-called Great Silence. Is this the true end, or does the universe hold another surprise in its still unknown laws? No one knows for sure. What we do know is that, on the largest and most distant scale, black holes will be the last protagonists of the cosmic story, silent witnesses of a universe that was once full of light. Have you ever wondered where the gold in your ring, the calcium in your bones, or the oxygen you breathe comes from? The answer is more astonishing than it seems. All the elements that make up our bodies and our planet were forged in the hearts of stars. The primitive universe only had hydrogen and helium, but cosmic alchemy began when the first stars ignited their nuclear furnaces and started transforming these simple ingredients into increasingly complex elements. In the core of a star, the pressure and temperature are so extreme that atoms fuse and create new elements. First, hydrogen is converted into helium. When the star exhausts its hydrogen, it initiates a chain of fusions that produces carbon, oxygen, neon, and other elements fundamental to life. But the true magic occurs when a massive star reaches the end of its life. Unable to support its own weight, it collapses and explodes in a supernova. This violent explosion releases such an amount of energy that it allows for the formation of even heavier elements, like gold, silver, and uranium. Thus, every atom of these precious metals is the remnant of an ancient stellar catastrophe. Does this mean we carry stardust within us? Exactly. Every cell in our body contains atoms that once formed part of a distant star. If we could travel back in time and observe the journey of a calcium atom, we would see how it was created in the last breath of a supernova, traveling billions of light years until it ended up on Earth and, ultimately, in our bones. Literally, we are children of the stars, connected to the cosmos through the matter that composes us. This stellar alchemy not only explains our existence, but also reminds us that the life and death of stars are part of an endless cosmic cycle. Each generation of stars enriches the universe with new elements, seeding the clouds of gas and dust where solar systems will be born and, perhaps, new forms of life. How many atoms in your body have traveled across entire galaxies before finding themselves here and now? The universe is a great laboratory of transformation, and all living beings are the result of that ancient and ongoing alchemy. How deep can we look into the universe? The answer is not only astonishing, but also revealing about our own existence. The so-called deep field is one of the boldest experiments in modern astronomy. It points a telescope at an apparently empty region of the sky and lets it collect light for entire days. What was found by doing this? Not just scattered stars, but thousands of galaxies, each with hundreds of billions of stars, in a portion of the sky as small as the head of a pin viewed at arm's length. Why is this finding so impactful? If that tiny fragment of the sky contains such a vast number of galaxies, how many are there in the entire observable universe? It is estimated that there could be more than 2 trillion galaxies, each filled with its own worlds, nebulae, and mysteries. The deep field forces us to rethink our perspective. What seemed empty is, in fact, an ocean of unreachable cosmic structures, separated by distances so immense that the light from some of those galaxies has taken more than 13 billion years to reach us. Does this mean we are seeing the past? Exactly. Observing the deep field is like looking at an old photograph of the universe, captured when it was still young, and the first galaxies were just beginning to form. It is a natural time machine. The farther we look, the further back in history we travel. Some of the galaxies we detect no longer exist as such. They have changed, collided, or vanished, but their light continues to travel through the cosmos, telling us stories of times we will never witness in person. The deep field is much more than an impressive image. It is proof that the universe is vast beyond all conception, and that most of its content remains hidden from plain sight. It reminds us that the darkness of the night sky is not empty, but the backdrop of an unfathomable cosmic play. Each point of light in that image represents an island of matter, energy, and possibly life, lost in the immensity. Who could imagine that by looking into nothingness, we would discover everything? What does it really mean for the universe to be expanding? Just over a century ago, the prevailing idea was that the cosmos was static and eternal. However, everything changed when Edwin Hubble, observing distant galaxies, noticed that their light spectra were redshifted. This phenomenon, known as redshift, is interpreted as evidence that those galaxies are moving away from us. It's as if the universe were a loaf of bread with raisins. As it bakes, the dough expands, and all the raisins move away from each other, even though none is the center. Thus, space itself stretches and galaxies drift apart. But when did this expansion begin? The answer takes us back to the Big Bang, the moment when everything we know was concentrated in an unimaginably dense and hot point. About 14 billion years ago, that tiny seed exploded, giving rise not only to matter and energy, but also to space and time itself. Since then, the universe has been continuously growing. However, it's not that galaxies are moving through space like ships sailing an ocean. Rather, the ocean itself, space, is expanding and carrying the galaxies along with it. At what speed does this expansion occur? This is where Hubble's constant comes into play, a figure that indicates how fast galaxies are separating based on their distance. The farther away a galaxy is, the faster it moves away from us. This means that if we could observe a galaxy far enough away, we would see it receding at speeds greater than that of light. This does not violate relativity because nothing travels through space faster than light. It is space itself that is stretching, and the future. Surprisingly, the expansion of the universe not only continues, but is accelerating. A mysterious force called dark energy seems to be driving this acceleration. No one knows exactly what dark energy is, but it accounts for about 3/4 of all the energy in the universe. If this acceleration continues, the most distant galaxies will disappear from our view, and eventually, the night sky will be much emptier and quieter. Thus, the expansion of the universe not only reveals our cosmic past, but also determines the ultimate fate of everything that exists. What is dark matter? If you've ever wondered why galaxies don't disintegrate while spinning at such high speeds, the answer has to do with this mysterious substance. Although everything we can see in the universe, stars, planets, gas, dust, is part of ordinary matter, astronomers have discovered that this only represents a small fraction of everything that exists. About 85% of the universe's mass is made up of dark matter, an invisible form of matter that neither emits, absorbs, nor reflects light. It is literally as if the universe is built on invisible foundations. How do we know it's there if we've never seen it? The evidence comes from its gravitational effects. When scientists observe galaxies, they notice that the stars at their edges are spinning too fast for the gravity of the visible matter to hold them together. It's like trying to throw a stone tied to a string, and the string isn't strong enough to keep it spinning. You would need something stronger, something invisible that provides more gravity. That something is dark matter. Furthermore, when light from distant galaxies passes near large clusters of matter, it bends in a way that can only be explained if there is much more mass than we can see. What is dark matter made of? That is one of the big, unanswered questions of modern science. It is not made up of atoms like the things we know. It does not form planets, stars, or clouds of gas. Several theories have been proposed. Perhaps they are exotic particles, never before detected, like WIMPs or axions. For decades, experiments in underground laboratories and space observatories have tried to capture some direct signal from these particles, but so far, we only have indirect clues. Could dark matter be the key to understanding the universe? Imagine trying to assemble a giant puzzle, but most of the pieces are transparent. You know they are there because the whole makes sense only if you include them, but you can't see or touch them. That is the search for dark matter, a global effort to uncover the hidden part of reality. Understanding it would not only solve one of the great cosmological mysteries, but could revolutionize physics, showing us an even stranger and more fascinating universe than we ever imagined. What is dark energy, really? If you've ever felt that the universe holds secrets that are almost impossible to decipher, this is surely the greatest of them all. Dark energy is a mysterious form of energy that fills all of space and seems to be accelerating the expansion of the universe. But how do we know it exists if we can't see, touch, or directly detect it? Its presence is inferred from astronomical observations, such as the movement of distant galaxies and the behavior of light from far-off supernovae, which reveal that the universe is not only expanding, but doing so at an ever-increasing rate. Why is this so surprising? For almost the entire 20th century, Scientists believed that gravity, with its attractive force, would slow down the expansion of the universe. However, by the late 1990s, astronomers discovered that galaxies are moving away from each other at an increasing speed. It's as if you were inflating a balloon, and instead of the air pressure decreasing, it suddenly increased mysteriously, causing the balloon to expand faster than expected. That invisible pressure driving the expansion is what we now call dark energy. But what exactly is this energy? No one knows for sure. Some scientists think it could be a fundamental property of space itself, a cosmological constant, as Einstein suggested, acting as a kind of anti-gravity. Others explore even more exotic theories, such as the existence of a new type of energy field that permeates the entire cosmos. The most puzzling thing is that, according to our best estimates, dark energy makes up about 70% of all the content of the universe. This means that of everything that exists, most is composed of something we don't even understand. How far can the influence of dark energy reach? Scientific predictions suggest that if it continues to dominate, the universe could expand forever, becoming colder and emptier. However, we do not know if its force will remain constant, increase, or even disappear over time. Each new discovery adds questions, not answers. Dark energy is, for now, the great cosmic enigma, a reminder that the universe is much stranger and more fascinating than we ever imagined. Did you know that the universe can vibrate as if it were the surface of a lake? When invisible stones, like black holes or neutron stars, collide in the cosmos, they generate ripples that travel through the very fabric of space-time. These ripples are the famous gravitational waves. But what does it really mean for space-time to vibrate? Imagine a taut sheet. If you place two heavy balls and make them spin around each other, the fabric deforms and those alterations propagate in all directions. Thus, every time colossal events occur in the universe, space trembles, and those vibrations cross the cosmos at the speed of light. For a long time, this phenomenon was just a theoretical prediction proposed by Albert Einstein in his theory of general relativity in 1915. No one could imagine how to detect something so subtle, as gravitational waves are incredibly weak. When they reach Earth, they stretch and compress space by a fraction smaller than the size of a proton. So how did we manage to hear them? The answer came in 2015, when the LIGO detectors in the United States managed to capture the echo of the collision of two black holes located over 1 billion light-years away. It was like hearing the rumble of thunder for the first time in a universe that until then seemed silent. Why are these waves so important? Because they open a window to invisible events. Light cannot escape from a black hole, but gravitational waves can. Every time we capture one, we are witnessing a kind of cosmic X-ray, a direct message from the most extreme and violent events in the universe. For the first time, we can study black hole mergers, neutron-star collisions, and even search for signals of unknown phenomena, all without needing to see the light they emit, because often, there simply is no light. Moreover, gravitational waves allow us to test the most fundamental laws of physics under extreme conditions. Are there exotic objects that challenge what we believe we know about matter and gravity? Could some of these vibrations reveal hidden dimensions or new particles? Each new detection is like a message in a bottle sent from the deep past of the universe, offering us clues about its history and structure. Thus, listening to gravitational waves is, in a way, beginning to understand the universe, not only by what we see, but also by what we hear in its subtle and profound rumble. What would happen if you got too close to a black hole? The answer lies in one of the most fascinating concepts in physics, the event horizon. This invisible boundary marks the point of no return. If you cross it, nothing, not even light, can escape. It's like a definitive cosmic border. On the other side, the universe loses contact with you forever. But why does this happen? The gravity of a black hole is so intense that it warps the space and time around it, creating an abyss from which there is no escape. To understand it better, imagine that space is a large elastic sheet. A massive object, like a star or a planet, sinks it a little, but a black hole punctures it to create a bottomless pit. The event horizon would be the edge of that pit. If you threw a ball from afar, you could retrieve it, but if you let it fall beyond the edge, it would disappear inside, with no chance of coming back. The same happens with matter and energy that cross the horizon. They are trapped forever. An unsettling question is what one would experience when approaching this limit. For a distant observer, it would seem like you are slowing down just before the horizon, becoming fainter and turning redder. However, for someone falling in, the crossing happens in an instant, without noticing anything special at that precise moment. But, past that boundary, the fate is sealed. Every trajectory inevitably leads to the center, where the known laws of physics cease to function. The event horizon is also crucial for the great enigmas of modern physics. Does information disappear inside a black hole? Is it destroyed forever? Or is there some way to recover it? This dilemma has led scientists to debate for decades, connecting quantum mechanics and general relativity in one of the deepest paradoxes of the universe. The event horizon not only marks the end of the journey for anything that crosses it, but it also represents the limit of our knowledge about the nature of space and time. What is capable of governing the heart of an entire galaxy? At the center of most galaxies, including our own, lies a cosmic monster, a supermassive black hole. These colossi can have masses equivalent to millions or even billions of suns, and their gravity is so intense that not even light can escape their embrace. But how do these titans of the universe form? It is not simply a matter of adding up stars. The answer is much more surprising and still not entirely clear. Some theories suggest they are born from the merging of smaller black holes, while others point to gigantic clouds of gas collapsing in the dawn of the cosmos. How do these supermassive black holes affect their galaxies? Far from being simple silent devourers, they profoundly influence galactic evolution. When they absorb matter, they release colossal amounts of energy in the form of jets and radiation, capable of expelling gas over enormous distances. It's as if the core of the galaxy ignites an engine that regulates the birth of new stars, halting or accelerating their formation depending on the amount of available material. Thus, the supermassive black hole acts as a conductor, setting the tempo for galactic development. Is it possible to observe any of these giants? Although we cannot directly see a black hole, astronomers have managed to detect their presence by observing the behavior of the stars and gas surrounding them. A fascinating example is Sagittarius A, the supermassive black hole residing at the center of the Milky Way. Its mass is equivalent to about 4 million suns, and thanks to decades of observations, we know that stars orbit around it at dizzying speeds, as if they were dancing frantically on the edge of an invisible abyss. Could supermassive black holes collide with each other? When entire galaxies collide, their central black holes can end up orbiting each other in a violent gravitational dance that culminates in a titanic merger. Such events release gravitational waves, vibrations in the very fabric of space-time, which we have already begun to detect from Earth. Thus, supermassive black holes are not only the silent guardians of their galaxies, but also protagonists of some of the grandest catastrophes in the known universe. What if I told you that there are true cosmic mirrors in the universe capable of showing you objects that would otherwise be invisible? This is the essence of gravitational lensing, a phenomenon that occurs when a massive object, such as a galaxy or a cluster of galaxies, stands between us and a distant source of light, like an even more distant galaxy or a quasar. The gravity of that massive object curves space-time, bending the rays of light and acting like a gigantic natural magnifying glass. Thus, we can see objects that are hidden behind that mass and even observe details that would otherwise be impossible to distinguish. Why does light bend? According to Einstein's general theory of relativity, gravity is not just a force, but a distortion of space-time. When light travels near a large concentration of mass, its path bends following that curvature. It's similar to how a ball rolls across a stretched sheet. If you place a heavy ball in the center, the sheet dips, and a smaller ball passing nearby will change its trajectory. In this way, light coming from a distant galaxy can take multiple paths around the massive object, reaching Earth from different directions. The result can be astonishing. Sometimes, gravitational lensing multiplies the image of the same object, forming arcs, luminous rings, and even multiple reflections, as if the universe were playing with funhouse mirrors. A famous example is the Einstein ring, where the light from a distant galaxy perfectly curves around a foreground galaxy, forming an almost complete circle. In other cases, a single distant object may appear as several separate images, allowing astronomers to study details that would be hidden by any other method. Why is this phenomenon so important? Gravitational lensing not only allows us to see further in time and space, but also reveals hidden mysteries. Thanks to it, scientists can study dark matter, that invisible substance that does not emit light, but whose presence is revealed by distorting the paths of light rays. Moreover, this effect helps measure the expansion of the universe and discover galaxies so far away that their light has taken billions of years to reach us. Thus, the universe gifts us, thanks to gravity, a window to the invisible, and a reminder that sometimes the greatest secrets are hidden just behind the veil of what we can see. How big can stars be in the universe? Hypergiant stars take us to the extreme of what is possible. They are true cosmic monsters, capable of challenging our imagination and the very laws of physics. Did you know that one of these stars, called Scuti, could contain within it not only our Sun, but more than 1,500 times its volume? If we placed it at the center of our solar system, its surface would extend beyond the orbit of Jupiter. Its size is so colossal that what is an unimaginable distance for us is barely its skin for a hypergiant. But size isn't everything. These stars are also incredibly luminous. For example, Eta Carinae, one of the most studied hypergiants, shines with a power equivalent to several million times that of the Sun. If it were at the same distance as Sirius, the brightest star in the night sky, its light would blind us. However, this brightness comes at a price. Hypergiants live fast and die young. While a star like our Sun can live for more than 10 billion years, a hypergiant barely reaches a few million before spectacularly collapsing. What happens when such a massive star reaches the end of its life? The outcome is often one of the most intense explosions in the universe, the supernova. In that moment, the star releases in seconds more energy than the Sun will emit in its entire existence. Some hypergiants can even produce hypernovae, even more colossal explosions that can give rise to massive black holes and scatter heavy elements, like gold and uranium, throughout the cosmos. In fact, without these explosions, many of the elements that form planets, and even life itself, would not exist. Why don't we see hypergiant stars with the naked eye in our sky? Despite their size and brightness, these stars are very rare and are usually found at enormous distances from Earth, hidden by interstellar dust. Often, their instability causes them to expel vast layers of gas and dust, forming nebulas that surround them and make observation difficult. However, they are key pieces for understanding the evolution of galaxies, as their brief but intense life transforms the environment around them and sows the raw materials for new generations of stars. Thus, these ephemeral giants are the alchemists of the universe, responsible for some of the most spectacular and fundamental chapters in cosmic history. What happens when two galaxies meet in the vast stage of the universe? Unlike what we might imagine, these encounters are not usually chaotic explosions where stars collide with each other. In fact, the space between stars is so enormous that even if one galaxy devours another, most of its stars pass by without touching. But then, why do we talk about galactic cannibalism? The answer lies in gravity and the inevitable fate of many galaxies, to devour one another, to grow and transform. Cannibal galaxies are true cosmic predators. They use their gravity to attract, distort, and ultimately absorb smaller or weaker galaxies. This process, which can last hundreds of millions of years, is fundamental to the evolution of the universe. Just like in nature, where larger predators feed on smaller ones, in the cosmos, massive galaxies engulf the tiny ones, merging their stars, gases, and dark matter. As a result, galaxies grow, change shape, and can trigger spectacular bursts of star formation, known as starbursts. Did you know that our own Milky Way is a cannibal galaxy? Throughout its history, our galaxy has incorporated several satellite galaxies. Astronomers have detected traces of these ancient victims in the form of stellar streams, like scars running through the galactic halo. And the most surprising thing is that this process continues. The Milky Way is currently in the process of devouring the Sagittarius dwarf galaxy and, in the distant future, will star in a monumental collision with the Andromeda galaxy. But will that be the end of galaxies as we know them? Not exactly. Although encounters are violent on a cosmic scale, they often lead to new, even more complex structures, like giant elliptical galaxies. If we look at the deep universe, we discover that galactic cannibalism is one of the main engines of cosmic evolution. Mergers and absorptions have shaped the galaxies we see today. Even the supermassive black hole at the center of many galaxies can grow by feeding on the material from engulfed galaxies. Without these encounters, the universe would be a much more monotonous and predictable place. Thus, the story of galaxies is largely a story of survival, transformation, and above all, cannibalism on a scale so colossal that it defies our imagination. Have you ever wondered how special the sun really is? Although for us it is the center of everything, in the vast cosmic catalogue it is, paradoxically, an extremely common star. The sun belongs to the category of yellow dwarf stars, scientifically known as spectral type G2V. There are billions of similar stars in the Milky Way. Its size, brightness, and temperature do not stand out as extreme. It is neither the largest, nor the hottest, nor the brightest. If the universe were a city, the sun would be like an average citizen, neither the tallest nor the shortest, but absolutely essential for those around it. But how does the sun compare to other stars? There are giant stars that could swallow the sun hundreds or thousands of times, like Betelgeuse or Antares, and others so tiny that they are barely faint spheres of gas. Our sun shines with a steady and serene light, unlike variable stars that flicker and fluctuate like cosmic disco lights. Moreover, its longevity is another of its virtues. It is halfway through its life, with about 4.6 billion years of existence and at least another 5 billion ahead, before transforming into a red giant and, finally, into a white dwarf. What about its location? The sun is situated in one of the spiral arms of the Milky Way, far from the bustling galactic center, where stars are born and die at frantic rates. This location is, curiously, an advantage for life. The central regions of the galaxy are exposed to intense radiation and cataclysmic events that would make the existence of habitable planets very difficult. Thus our sun, in its apparent normality, offers stability and protection like a quiet neighborhood in a chaotic city. However, this common inhabitant of the cosmos is, for us, the source of all the energy that sustains life on Earth. Every second, the sun fuses approximately 620 million tons of hydrogen into helium, releasing an unimaginable amount of energy. The light that warms us and allows plants to grow takes just over 8 minutes to travel the 150 million kilometers that separate us. Thus, although the sun is an ordinary star from a galactic perspective, for our small planet, it is the difference between life and nothingness, between the vibrant blue of the oceans and the cold darkness of space. Are there other worlds where life could thrive? Humanity has dreamed for centuries of the possibility of not being alone in the universe, but only in the last few decades have we had the technology to seek concrete answers. Exoplanets, those planets that orbit stars outside our solar system, have become the protagonists of one of the most exciting scientific quests of our time. Thanks to telescopes like Kepler and TESS, we have confirmed the existence of thousands of exoplanets. But how many of them could actually be habitable? A habitable exoplanet, in simple terms, is one that is located in the so-called habitable zone of its star, a region where temperatures would allow for the existence of liquid water on the surface, as occurs on Earth. But is liquid water enough for life to emerge? Not necessarily. Many more ingredients are needed: a stable atmosphere, protection from radiation, essential chemical elements, and preferably a star that is not too violent. It's like baking a cake. Having flour and sugar is not enough. You also need the right temperature and just the right amount of time in the oven. One of the most famous star systems in the search for habitable exoplanets is TRAPPIST-1, where 7 Earth-sized planets have been identified, 3 of them within the habitable zone. Does this mean they are twins of our world? Not necessarily. True habitability depends on complex factors: atmospheric composition, the presence of water, the activity of the star, and even the tilt of the planet's axis. Even with all this, we have not yet detected clear signs of life. Are we searching in the right place? Or perhaps life is much rarer than we imagine? The search for habitable exoplanets also forces us to rethink what we understand by life. Could there be forms of life based on other elements, like silicon, instead of carbon? Or beings that thrive in oceans of liquid methane, like on the moon Titan? Each discovered exoplanet is like another piece of a gigantic cosmic puzzle. Although we have not yet found a second home, the mere fact that there could be billions of worlds in conditions similar to those of Earth invites us to look at the sky with renewed wonder. Perhaps, in some distant corner, life is flourishing, waiting to be discovered. What happens when a star dies near us? To answer this question, let's mentally travel back to the year 1987. At that time, astronomers around the world were astonished when, in the Large Magellanic Cloud, a neighboring galaxy located 168,000 light-years away, a supernova made its appearance. It was named Supernova 1987A, or simply SN 1987A. Why was it so special? Because it was the closest supernova explosion observed since the invention of the telescope, and the brightest visible from Earth in nearly 4 centuries. One might think that such a close supernova would be a terrifying spectacle or a danger to life on our planet. However, despite its violence, the distance was enough for us to only receive an impressive flash of light and an invaluable dose of scientific information. The light from the supernova took over 160,000 years to reach us. So what we saw in 1987 was the death of a star that occurred when humans were just beginning to develop language. What did we learn from this explosion? For the first time, scientists were able to detect neutrinos coming from a supernova, tiny particles that travel almost at the speed of light and rarely interact with matter. It was like receiving a letter written directly by the core of the star at the moment of its collapse. Supernova, 1987. It also allowed us to observe, in real time, how a massive star can transform the surrounding gas and dust, creating bright rings that are still being studied today. Did you know that, thanks to this explosion, we were able to better understand what stars are made of and how heavy elements are dispersed throughout the universe? Elements like gold, iron, or oxygen, essential for life, are forged in the heart of these cosmic catastrophes and are thrown into space in every supernova, seeding future generations of stars and planets. But what remained after such an explosion? For years, astronomers have searched for the remnant, the collapsed core of the star, hoping to find a neutron star hidden among the dust and gas. Although recent hints suggest that it might be there, it has yet to be directly detected. The search remains open, and each new observation reminds us that, even at unimaginable distances, the most violent events in the cosmos can be the key to understanding our own origins. Thus, the closest recorded supernova not only illuminated the night sky, but also the path of human knowledge about the cycle of life and death in the universe. How powerful can magnetic forces be in the universe? If you thought the magnets on your refrigerator were strong, wait until you meet magnetars. These neutron stars are the objects with the most intense magnetic fields ever discovered. To put it in perspective, a single magnetar can have a magnetic field up to 1,000 trillion times more powerful than Earth's. If you could bring such a powerful magnet within a few 100,000 kilometers, it would strip the information from all credit cards and even disintegrate the very atoms of your body. But how can something so extreme arise? Magnetars are born in the hearts of massive stars that explode as supernovae. After the collapse, the dense core leaves behind a neutron star, but on rare occasions, this remnant spins so fast and possesses such an amount of energy that it creates a monstrous magnetic field. It's as if nature decided to take the concept of magnetism to the limit. In comparison, if Earth were a compass, a magnetar would be a city-sized electromagnet turned up to the max. This field is so strong that it distorts the star's very surface and affects the space around it, generating phenomena that challenge our understanding. And what happens when a magnetar releases energy? Outbursts known as flares occur, so intense that they can traverse entire galaxies. In 2004, one of these outbursts reached Earth, and although we were over 50,000 light-years away, sensors on our planet detected it as the brightest flash seen outside the solar system. If such a magnetar were just a few light-years away, it could wipe out our planet's atmosphere in seconds. Scientists believe these flares occur when the rigid crust of the magnetar, under the pressure of its own magnetic field, suddenly cracks, releasing colossal amounts of energy in the form of gamma rays and X-rays. But magnetars are not only surprising for their destructive power, they are also natural laboratories for studying physics under conditions impossible to replicate on Earth. In their vicinity, matter and light behave in completely new ways. Atoms deform, light can bend, and even change color. These extreme conditions allow astronomers to test the most advanced theories about matter and magnetism. Thus, magnetars not only show us the fiercest side of the cosmos, but also offer clues about the limits of the physical laws that govern the universe. Where does the solar system really end? Although we often think it consists only of the planets and the sun, the truth is that our cosmic neighborhood extends far beyond, delving into regions inhabited by icy and mysterious bodies. Two of these regions, the Oort cloud and the Kuiper belt, are true relics of the solar system's origins, guardians of secrets we are just beginning to uncover. The Kuiper belt lies beyond Neptune's orbit and is like a wide, flattened ring made up of billions of small objects, most of which are composed of ice and rock. Did you know that Pluto, the famous dwarf planet, is just one of the largest inhabitants of this belt? Eris, Haumea, and Makemake also reside there, bodies that remind us that the solar system is much more varied than what we learned in school. The Kuiper belt is, in a way, a museum of the sun's childhood. Its objects are intact fossils of planetary formation, preserved for billions of years at such low temperatures that chemistry barely changes. But what lies beyond? The Oort cloud is an even more distant and mysterious frontier. Imagine a gigantic sphere completely enveloping the solar system, extending more than a light-year away from the sun. It is believed that the Oort cloud houses trillions of comets, silently waiting in the darkness. From time to time, some disturbance, perhaps the passage of a nearby star, pushes one of these comets inward into the solar system, gifting us with celestial displays that have amazed humanity since ancient times. However, no object from the Oort cloud has been directly observed. Its existence is inferred from the trajectory and origin of long-period comets that traverse our sky. What is the significance of these two regions? Beyond containing the largest reserve of frozen water in the solar system, both the Kuiper belt and the Oort cloud are natural laboratories that could explain the origin of water on Earth and even the emergence of organic molecules. It is thought that comets from these areas may have seeded our planet with the basic ingredients for life. Thus, every fragment of ice traveling from the outskirts of the solar system carries clues about how it all began. In short, The Kuiper Belt and the Oort cloud reveal that the solar system is much more extensive and complex than we usually imagine. They act as time capsules, preserving traces of the past and reminding us that, at the sun's borders, there are still mysteries to explore. What other secrets await in the icy depths, waiting to be discovered by future explorers? Is it possible for two people to experience time differently, even while being in the same universe? The answer, although it may seem like science fiction, is yes. According to Albert Einstein's theory of relativity, time is not a universal constant, but can stretch or compress, depending on two key factors: gravity and speed. When an object approaches a source of extreme gravity, like a black hole, time for that object passes more slowly compared to someone who is far from that gravity. It's as if the clock next to a black hole ticks more slowly, while on Earth, seconds pass at a normal pace. But what happens if we travel at speeds close to the speed of light? This is where time dilation due to speed comes into play. The faster you move, the slower time passes for you compared to someone who is stationary. It's the famous twin paradox. If one of the twins embarks on a spaceship and travels at a speed close to light while the other remains on Earth, when the traveler returns, they will have aged much less than their sibling. Thus, time is not only different depending on location, but also on the speed at which you move. How can we imagine this in daily life? Think of time as an elastic band. For most of us, the band is relaxed and time flows normally. But if we approach a very massive object or accelerate to incredible speeds, that band stretches or compresses. In fact, GPS satellites orbiting Earth must constantly correct their clocks to compensate for these effects, as they experience less gravity and greater speed than on the Earth's surface. If they didn't, their measurements would be completely inaccurate within minutes. Does this mean we could travel to the future? In a way, yes. If a person could get close to a black hole or travel at extremely high speeds, they would experience time much more slowly than the rest of humanity. Upon returning, they would find that many more years have passed for everyone else. This phenomenon is not just a mathematical curiosity. It has been experimentally confirmed with atomic clocks on airplanes and satellites. Thus, the universe reminds us that time, far from being absolute, is as relative as space itself, and that our passage through it depends on where we are and how fast we are moving. Is it possible for a dead star to become one of the most precise clocks in the universe? This is how pulsars work. Remnants of massive stars that, after exploding in a supernova, collapse into incredibly dense and small objects known as neutron stars. But some of these objects, instead of remaining silent, spin at breakneck speeds, emitting beams of electromagnetic radiation from their magnetic poles. Every time that beam points towards Earth, we detect it as a regular pulse, almost like the ticking of a cosmic clock. How precise are they? Some pulsars rival Earth's atomic clocks, falling behind by only a fraction of a second over millions of years. How do they manage to emit such precise and powerful signals? It all comes down to their incredible magnetic field and rapid rotation. A typical pulsar can spin anywhere from several times per second to hundreds of times in that same span. To put it in perspective, imagine a sphere about the size of a city, but with a mass greater than that of the entire Sun, rotating so fast that if Earth did the same, the centrifugal force would launch us into space. This combination of mass, density, and speed generates magnetic fields trillions of times more intense than those of our planet, and it is that extreme magnetism that channels particles and creates the famous beams of radiation. What are pulsars good for besides being a wonder of physics? They have been fundamental to some of the most groundbreaking discoveries in modern astronomy. For example, thanks to the regularity of their pulses, astronomers have been able to measure distances in space with extraordinary precision, detect gravitational waves, and even verify predictions of Einstein's theory of relativity. In 1974, a message was sent into space, using the frequency of a pulsar as a reference, hoping that an intelligent civilization could decipher it. Did you know that there are pulsars that are part of binary systems, orbiting in pairs with other neutron stars or even black holes? These systems are true cosmic laboratories, where the laws of physics are pushed to the limit. When two pulsars spin around each other, their gravitational dance can cause the emission of gravitational waves, those ripples in the fabric of space-time that we have only just begun to detect on Earth. Thus, pulsars are not only the beacons of the cosmos, but also the keys to understanding some of the deepest mysteries of the universe. What if I told you there is a number capable of measuring the speed at which the universe itself is expanding? That number is known as the Hubble constant, and it is one of the most important keys to understanding the history and fate of the cosmos. But how was this mysterious constant discovered, and why does it continue to be a topic of debate among astronomers? The journey begins nearly a century ago, when Edwin Hubble observed that galaxies are moving away from us, and that the farther they are, the faster they move away. This seemingly simple relationship revealed that the universe is not static, but rather expanding. The Hubble constant can be imagined as the speedometer of the universe. If space were a loaf of bread in the oven, the raisins embedded within the bread would be the galaxies, and the expansion of the bread would cause them to move apart from each other. The constant answers a fundamental question. At what speed are galaxies separating due to the expansion of space? Expressed in kilometers per second for every million parsecs, its value allows us to calculate, for example, the approximate age of the universe and the distance to distant galaxies. However, this is where the story gets complicated. Shouldn't it be simple to measure a single number? In practice, it is not. There are two main methods for calculating the Hubble constant. One measures the nearby universe, using supernovae and Cepheid variables as standard candles. The other analyzes cosmic microwave background radiation, the echoes of the Big Bang. Surprisingly, these two paths give us slightly different results. Why does this happen? Are we facing a measurement error or a hidden clue about new physics that we do not yet fully understand? The difference in the values of the Hubble constant, although small, has sparked one of the most fascinating discussions in modern cosmology. If the universe is expanding faster than current models predict, it means there may be unknown ingredients in its composition or in its early stages. Solving this enigma is crucial. The Hubble constant not only affects our understanding of the past, but also how the future of the universe will unfold. Will it expand forever? Will it slow down at some point? Each new measurement is another piece in the cosmic puzzle, and the quest to decipher it is undoubtedly one of the great scientific adventures of our time. What if our universe is not the only one? This is the question that drives one of the most fascinating and debated ideas in modern cosmology: the existence of multiverses. According to this hypothesis, our universe would be just one among many others, each with its own physical laws, fundamental constants, and even spatial and temporal dimensions. Just like bubbles forming in a gigantic pot of boiling water, each universe could arise and expand independently, never interacting with the others. But where does this idea, seemingly taken from science fiction, come from? The inflationary theory, which explains the rapid initial expansion of the universe after the Big Bang, gives us a clue. Some cosmologists suspect that inflation may not have occurred just once, but is eternally repeating in different regions of space. This would lead to an inflationary multiverse, where each inflated bubble is an autonomous universe, perhaps with completely different physical laws. For example, in one of those universes, gravity could be stronger. In another, atoms might not exist. And in yet another, life could be impossible. But the possibilities don't end there. Quantum mechanics, with its mysterious probabilistic nature, also opens doors to imagining multiple universes. According to the many worlds interpretation, every time a quantum event occurs with several possible outcomes, the universe splits, creating a new reality for each alternative. In other words, in some corner of the multiverse, there exists a universe where you made different choices than the ones you made today. Could we ever have evidence of these other universes? It's one of the great unknowns, because if they exist, They would be separated from us by distances and realities that are unreachable. Does this mean that everything we imagine actually happens in some parallel universe? Some scientists warn that, although the idea of multiverses is attractive and elegant, there is currently no direct evidence of their existence. However, multiverse cosmology helps answer profound questions. Why do the laws of physics seem so finely tuned to allow life? Is our universe special, or just one among infinite possibilities? Although for now, multiverses are a speculative frontier of science, their study invites us to expand the limits of our imagination and to question whether what we call reality is just a small part of a cosmos much vaster and stranger than we could have ever dreamed. What does destiny hold for the universe? This is one of the deepest questions humanity can ask. Our existence seems fleeting when compared to the life of the cosmos, but scientists have dedicated decades to deciphering the final scenarios that could await everything we know. The answer, far from being simple, is as fascinating as it is unsettling. One possible outcome is the so-called Big Freeze. According to this scenario, the accelerated expansion of the universe will continue indefinitely. Galaxies will drift apart until the distance between them is so vast that light takes longer than the age of the universe to travel from one to another. Stars will eventually burn out all their fuel and slowly extinguish, leaving behind white dwarfs, neutron stars, and black holes. The remaining matter will cool down until it approaches absolute zero. In this future, the universe will become a cold and dark place, where even atoms will be unable to form complex structures. It's as if the entire universe is slowly shutting down, immersed in an endless night. But there is another equally surprising possibility: the Big Rip. If dark energy, that mysterious force driving the expansion of the universe, increases uncontrollably, the very structure of space-time could tear apart. Galaxies, solar systems, planets, even atoms, everything would be separated by an unstoppable expansive force. Could the universe self-destruct from within, as if it were being stretched until it breaks? Although it sounds almost apocalyptic, scientists are still studying whether this fate is truly possible. On the other hand, there are those who propose the opposite scenario: the Big Crunch. In this model, universal expansion would slow down and eventually all matter and energy would be pulled back by gravity, collapsing into an extremely dense and hot point, perhaps giving rise to a new Big Bang. If gravity ultimately overcomes expansion, could we be living in an eternal cycle of universes that are born and die over and over again? Although none of these scenarios will occur in the near future, we're talking about times that far exceed the lifespan of the Sun and our galaxy. Thinking about the final fate of the universe invites us to reflect on our place in the cosmic vastness. Will the universe be a cold tomb, a final explosion, or an endless cycle? While we still do not know the definitive answer, each scientific discovery brings us a little closer to the frontier of our knowledge, reminding us that, despite our smallness, we are privileged witnesses of this cosmic journey. Is it possible to encompass the vastness of the universe with just words? When we look up on a clear night, we may not think about it, but we are faced with a story of billions of years, filled with mysteries yet to be solved and wonders we are just beginning to understand. Why is there something instead of nothing? What unknown forces govern the fate of galaxies and the matter that composes us? Each question about the cosmos brings us back to our own smallness and, at the same time, to the infinite curiosity that drives us to explore. The universe is more than just a backdrop of stars and planets. It is a natural laboratory where elements are forged, where time and space intertwine, and where the laws of physics challenge our imagination. From the tiniest particles to colossal structures, everything is connected in a cosmic dance. Isn't it astonishing to think that the calcium in our bones or the iron in our blood was created in the hearts of stars that exploded millions of years ago? We are, literally, stardust, traveling on a planet that orbits a common star in a galaxy among billions. The universe is not only vast in size, but also in mysteries. Despite centuries of observation and discovery, we continue to stumble upon fundamental questions. What is the dark matter that holds galaxies together? Why does dark energy accelerate the expansion of the cosmos? Are we alone in this immense ocean, or are there other worlds with life waiting to be discovered? Each answer opens new doors, and for every certainty, even more questions arise. But perhaps the most fascinating thing about the universe is not its vastness, nor its enigmas, but the simple fact that we can peek into them. Our ability to ask questions, to seek patterns in chaos, to marvel at the unknown is in itself a cosmic miracle. How far can we go? What will we discover tomorrow? The only certainty is that the universe will always hold secrets, and that the adventure of exploring it has only just begun. Thus, every night under the stars is an invitation to keep asking questions and to remember that deep down, we are witnesses to an extraordinary journey through time and space.